monitor today, so someone's going to have to tell me. If someone from NPlan can like read out questions in the chat, that'd be really useful.
I will, Peter.
Okay, thank you. Okay, can everyone see the slideshow?
Yes.
Okay, I might close this. Okay, welcome to this presentation on Markov chain Monte Carlo. So, next slide. So this slideshow, it goes through a couple of different topics. One of them is why did I choose this paper, and more form like it's actually more like why did I choose to do a paper on Markov chain Monte Carlo. Then I go into some background on Markov chains because that's a really important part of MCMC. And then I go through I explain in more depth like what is MCMC. Then I introduce accept reject sampling, which is not actually Markov chain Monte Carlo, but it actually is another algorithm that does the same thing. And I think it's a good starting algorithm to know about. And then I go into Metropolis Hastings sampling, which is Monte Carlo Markov chain sampling. I don't go into theory about, well, actually we can talk about this at the end. I have another slide on it. Okay, so why did I choose this paper? So there's there's different types of optimization that we use these days as machine learning practitioners. Or sorry, there's one main one that we use these days, which is gradient-based optimization. That's what's used for deep learning. The like most famous type of gradient-based optimization for deep learning where you have a ton of data is called stochastic gradient descent. But there's actually a lot of other methods for optimizing models. And I think because deep learning has become so popular that unless you're doing a degree in a field where those other forms of optimization are like tried and tested and used quite often, maybe like resource optimization, like some kind of systems degree, you don't actually see these other forms of optimization, and we almost never use them. So like I feel that if I were to give a percentage of the amount of time I use some kind of gradient-based optimization versus others, it's probably like 95% of the time I'm using gradient descent for whatever I'm doing. But there's a lot of other methods. So like another method is another like kind of fundamentally different type of optimization is called sampling-based optimization. And an example of that would be genetic algorithms, but there's a ton. There's one that's like really effective that I've used before, but you never see it, but I think that people have used it before also. It's called like the cross entropy method. So if you're ever looking for like a really simple way to use sampling to optimize something, I'd check that out. And then there's grid-based optimization methods. So a sampling method is like maybe I'll just add a little something beneath here. Is like the basics of an optimization problem are something along the lines of like, let's just say max, it could be min, and then you have some function, and then you have a domain like x is in big X, which is your domain. I know this is really quick, but we'll just and I just click slideshow, will it present again? Yeah. Okay. So yeah, your basics of your problem, and you're trying to find the X in your domain X. There's a lot more detail, like you could have constraints and all that stuff, but let's keep it at this level. Like for the optimization problem, your goal is to find the X that maximizes your function f. And so the gradient-based method will take the derivative of that function to find the optima, like the best point. The sampling-based method will put a probability distribution on X and then sample from it in order to choose which points to check, and it will choose the best one. And then the grid-based method will put some kind of grid on X in order to explore X. So there are different methods of exploring X to find the best F. So yeah, the best function value, and more specifically, like the X that does that. Is there a question?
Yes. So the question from me would be, when you sort of faced with a problem, like an optimization problem, is there a prescribed way of deciding which strategy is most applicable to a given problem? Like how would you normally decide which optimization approach is appropriate?
I wouldn't consider myself an expert in optimization, but I was going to go, and then I wanted to talk about the curse of dimensionality and how, and like why it relates to the reason why we're doing gradient-based descent for everything. So maybe that will give you a little bit of an answer. But if you want to decide exactly, I think it has a lot, like one thing to consider is like whether you already have a probability distribution over your domain that you want to optimize with respect to. So like maybe not every single point in your domain is equally likely. Then you probably would want to use some kind of sampling-based optimization, as long as you know that distribution. Maybe with a gradient-based optimization, because there's like versions that combine these two things, these different fundamental types of optimization. But so the curse of dimensionality is basically as like the number of dimensions in your domain increases, the size of the domain increases exponentially. It just maybe even it increases exponentially. And what that means is that exploring the domain becomes like much harder. So being able to using a grid or sampling based method becomes much harder to make sure that you feel comfortable that you've explored it such that you found like an optimal point. But with a gradient-based method, I mean, with a gradient-based method, not stochastic gradient descent, although there are there's some theory around that it's also true. You know that you're going to converge to at least a local minima. It might not be the best point, but you know it's a local minima. So around that point, it is the best point. But with these other two methods, as the domain gets larger in dimensionality, it's harder. You don't know if you've converged to a local minima with what you found, and maybe you can't find a good. It becomes much harder to explore the space. So that's actually the reason. Since we're using such large models, like I don't know, think of the large language models we're using. They have like 70 billion parameters. That means that our domain is of dimension 70 billion. And so I think it's a lot more comforting to know that at least with gradient descent, you're moving towards a local minima than if you were using these other methods where you're not sure. So I think that's a big reason. And I think empirically, we're just seeing better results using gradient-based methods for high dimensionality. Otherwise, if we didn't see it empirically, we wouldn't be doing it. But that's more of an explanation of why we tend to use gradient-based methods. So maybe to answer your question, it seems, at least empirically, that as the dimensionality of the problem increases, it's more likely that the best method is gradient-based.
That makes sense.
Yeah. But there's a ton of problems that I think we're so used to these high dimensional problems that are just like fitting massive models that can be done with smaller, like I'm all for going back to smaller models and trying to solve problems with them and using these other methods. In fact, the whole reason why I was working on this is because there's a personal project I'm working on where I want to use a sampling-based optimization method. So back here, there's three fundamental different types of optimizations: gradient-based, sampling-based, and grid-based. How is this related to Markov chain Monte Carlo? So Markov chain Monte Carlo is a technique for sampling from a distribution when we don't fully know the probability distribution. So say we wanted to use a sampling-based optimization method, but we don't actually know the distribution that we want to sample completely, we just know something about it. So it allows us to sample from these types of distributions, which means we can use sampling-based optimization methods to solve problems. So this is the reason why I am interested in it. There's actually a lot more applications to MCMC than enabling us to use sampling-based methods for optimization. This is the reason, so just to be clear, this is the reason why I'm interested in it. There's other reasons as well. So what kind of probability distributions can you sample from using MCMC? Or like, what knowledge do you have to know and what don't you have to know in order to sample from these distributions? So focusing on continuous distributions, we know that like one of the fundamental laws of probability distributions is for continuous distributions is if you take the integral of the distribution over the domain, it has to sum to 1. But say instead of knowing the actual probability distribution, you know some function x that when divided by some constant z is equal to p of x. So the probability distribution you care about. So z is a normalizing constant. And because it's constant, well, the important thing is that it's a normalizing constant. And the thing is, you don't know it. And probably the reason why you don't know it is because we don't know how to calculate the integral of f of x over the domain. Which is it happens a lot more than you would think. We just don't see it that often in the stuff we're doing. So MC applies when you know f of x, but you don't know how to calculate the normalizing constant. And then you can still sample from this distribution p of x even then, which I actually find kind of magical. And hopefully when I show you the algorithms, you'll see why it's so cool. So I've given you like a more theoretical or conceptual reason of how MCMC is useful, but like I wanted to give you a practical situation. So the practical situation that I'm using it for is Bayesian inference of common filter parameters with hidden states. Basically, so that's a lot of technical jargon, but the main thing is I want to learn a common filter. And the hard thing for me is calculating this algorithm where you want to calculate, if theta is the parameters of your model, you want to calculate this integral, in order to calculate the most likely parameters, so the distribution of parameters given your data and your prior. But we don't know how to calculate this integral, but we can calculate it with MCMC. And I just wanted to do an aside on common filters because I want to ground this in like why this kind of thing is so useful. What are common filters used? Like common filters with state spaces where you don't know the states. They're used in camera localization and computer vision. And more generally, they're used for removing noise from data. They're used a lot, and this was actually the first use case of common filters was in missile navigation, but like automated navigation of spacecrafts as well as other robotic systems. They're used like in a ton of places in financial time series forecasting. And then they're also used in tracking objects. So besides navigation, also in tracking objects. And the cool thing is that you can, using multimodal sensors, so you could use like maybe like a depth sensor and a camera, or I don't know, like GPS as well as a camera and stuff, like multimodal, meaning like from different modalities of data that you can combine to do this type of stuff. So common filters are used a lot in our world. Like they're in a lot of systems that we use. And this, you can use MCMC to deal with learning the parameters of a common filter. So it's quite powerful knowing how to use this method if it makes sense for your application. So before we go into Markov chain Monte Carlo, I wanted to talk about Markov chains, because there's some fundamental concepts that you need to know about Markov chains to understand Markov chain Monte Carlo. So what is a Markov chain? From Wikipedia, it says, Markov chain or Markov process is a stochastic process describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. Yeah, I wanted to read that out, but I don't feel like me reading that out should give you a good understanding of what a Markov chain is. We'll start there. But I underline stochastic process because I'm like, okay, well, what if you don't know what a stochastic process is? Which was definitely, that happened. I didn't know what it was the first time I heard of a Markov chain. And then you go to Wikipedia for what is a stochastic process. It says, in probability theory or related fields, a stochastic or random process is a mathematical object usually defined as a family of random variables in a probability space where the index of the family often has the interpretation of time. So I actually think this is an even more useless definition of a stochastic process than the Markov chain one is. The Markov chain one is okay, because I think stochastic processes were originally only like time-based processes, and then they got generalized in the field of mathematics. So if you're an expert in stochastic processes, you have to give this more general definition. But I would prefer that we focus on a simpler interpretation. So a stochastic process is a time series of random variables, where there's dependencies between the different. I don't know if there has to be dependencies between the random variables at each time step, but I'm guessing there might have to be. So here's an example of a stochastic process where, with respect to time, so you can see that, for example, the random variable x at t of +1. Oh, so this is a graphical model describing the dependencies between random variables in a stochastic process, meaning that the arrows describe dependencies. So you can see that x of t +1 is dependent on x of t. X of t +2 is actually dependent on all of the variables here. And I wanted to ask anyone, if the index is time, if they can see anything wrong with this graphical model.
Well, the x at t +3, sorry, the t +2 is dependent on the future event, which that makes no sense.
Yeah, exactly. That breaks causality, which is like a basic tenet of time, that you can't, a past event can't be based on a future event. I think that breaks down at like in quantum physics, but I'm not sure. If there's any quantum physics experts, let us know. But so yeah, this is actually an invalid stochastic process if the index is time. And we're only talking about stochastic processes where the index is time. So this is a stochastic process, but it's not a Markov chain. And the reason why it's not a Markov chain is because x of t +2 is dependent on x of t +1 and x of t. I think that, yeah, and what that means is that, like, if you need knowledge of x of t as well as x of t +1 to determine the probability distribution of x of t +2. And that's not Markov. Yeah, go ahead.
So does the Markov imply then that it's only dependent on a single previous state?
Yeah, not only a single, but the previous state.
Right.
So
there were like two, I don't know, two different states, I guess, simultaneously at the same time step. Like, say at t +1, there was like a variable y at t +1, and then it wouldn't be a Markov if x t +2 was dependent on both the x t +1 and the y t +1.
Well, so instead of thinking, this really depends, and we'll go into this in a second. This depends on your definition of state, what the state of the process is. So the state of the process should be X and Y. And X could be like, is usually maybe a vector, or it can be anything like this. X in this diagram, it could be an image, it could be a vector of size 5, it could be a single number. But your state is would be all of those, like whatever that your state is defined at. So like if X is an image, then X of t is an image, X of t plus 1, X of t plus 2 is an image. And if, yeah?
X describes like the overall state of this, I guess, the system.
Yeah, exactly.
Okay, that makes sense. Yeah, so only the one previous. You can't have like two realities in the
Yeah, exactly. Another
the chat. So I'll read it out. So can't I combine previous states into an extended state that only single previous state, and therefore it becomes a Markov?
Yes, you can. That's a common trick to incorporate more information about the history and still have a Markov chain. You see it a lot in like reinforcement learning. Actually, where you see it the most is when you go from decision-making theory to decision-making theory under uncertainty. There's a lot of math around taking into account more than just the previous state. That's a good question. And so the difference between a stochastic process and a Markov chain in terms of the graphical model is it would look something like this, where the only arrow pointing to any state is the previous state. So now I wanted to talk a little bit, and we touched upon it for a second, about the state space of a Markov chain. So X at any given time can take on values. And here, this could be an example of the state space of a Markov chain. So the state space is two numbers, and at any time it could be one of these states. So it could be 2, 0, 1, 1, 1, 2. And the arrows in this diagram actually show you which states you can go to from the state you're currently in. But that's not important. I wanted to introduce this idea of a state space. So for Markov chains, you could think of like the state with respect to time, the state at any given time has a set of values. Those values are within the state space of the Markov chain. I hope that makes sense, because it's an important thing to know. And so I wanted to give some examples of what like a Markov chain could look like. So you have a state space that's the numbers 1 to 1,000. Then your Markov chain would be like the first one is 1, 3, 4, 9, 9, 7, whatever I wrote just here. And I just gave a couple of examples of what the time series could look like. And these all depend on like the transition matrix between states, which we don't know. But the important distinction is that like the state space is the numbers 1 to 1,000, and then like xt or x0 in the first example is 1, x1 is 3, x2 is 4, and so on. So that's how the state space looks in a Markov chain. You have a value from it at each time step. And the important thing, the important concept to know in order to understand Markov chain Monte Carlo is a Markov chain's stationary distribution. And this is a concept that's a little bit harder to understand. So the stationary distribution of a Markov chain is a distribution where the frequency of states in the series remains constant over time. I actually wrote that. I didn't take it from Wikipedia, so I don't expect, and I just wanted to have something there, but I think it's much easier to understand what a stationary distribution is with examples. So like I said before, in the first example, you can see that after a certain point, the numbers in the Markov chain start being the same and that they have a repeated pattern. So let's assume that 5, 6 goes on for infinity. Then the Markov chain distribution has converged to the Markov chain is converged to a stationary distribution that only contains the states 5, 6, and they appear with frequency half-half, because one always happens after another. Another example would be in the second one, where there's some almost random set of numbers, or like the frequency of the numbers doesn't seem to repeat, and then you have the numbers 2, 4, 6, 8, which repeat over and over again. And so the thing I wanted to make clear by showing these two examples is that the sequence of the numbers after a certain point doesn't have to be the same. It doesn't have to be like 2, 4, 6, 2, 4, 6. It's the frequency at which they occur. So like there's 4 numbers and they should all occur 1/4 of the time based on the way I wrote this. That's what makes a stationary distribution a stationary distribution. So the idea that, let me see if I have it in the next slide. Yeah, okay. And then for the last time series, there's actually no stationary distribution, or at least it's not obvious that there's one because there's no repeated pattern within the series, or like there's no repeated frequency of states. Here's another diagram of a Markov chain and calculating the stationary distribution, or showing that it's stationary, where you have the transition matrix. Actually, maybe this is bad because I think I'm going into too much detail, so we're going to just skip that. So some ideas about Markov chains, some important details about Markov chains that I'm not going to give details about. So important facts without details is that a Markov chain can have multiple stationary distributions, meaning that depending where you start from, like the state you start from in your Markov chain, you can converge to multiple different distributions. Not always, but it can happen. And also, Markov chains do not always converge to a stationary distribution. Those are important things to know why Markov chain Monte Carlo is so cool and important. But the key idea, the main thing that I'm hoping that you can take away from this whole thing on Markov chains is this idea of a stationary distribution, which is after a certain, oh, is there a question?
There is a comment, and the comment says, it is worthwhile to add that the idea of stationary distribution is related to ergodicity. So in effect, you can get from every state to any other state in some time horizon.
Yeah, I'm trying not to go too deep into Markov chain theory, but maybe next time, because I want more of like the conceptual or intuitive understanding that like you start seeing the frequency of values starts to repeat itself, or like it stays the same.
Yeah. So I have a question. So why would we care about this frequency of repeated values? Like what's the utility of knowing it?
Okay, we'll get to that. It's a really good question. So just to show you, Markov chains can have multiple stationary distributions, and Markov chains do not always converge to a stationary distribution. So what is Markov chain Monte Carlo? Like, why are we talking about it? Or like, how does it work? So just as a reminder, the goal is to sample from some probability distribution P of x, where we only know f of x, where f of x is related to P of x by this equation here, and z is a normalizing constant. So Markov chain Monte Carlo is a method that constructs a Markov chain which converges to the stationary distribution P of x. So the reason why we care about this, like about stationary distributions and MCMC, is that we can get samples from P of x by using MCMC, because the stationary distribution of the Markov chain that you're sampling from to get that you're sampling from is P of X. So that means the big thing is like MCMC allows us to get samples from P of X without knowing P of X, only knowing F of X, which means we can do all kinds of things with like useful things with the samples. Like you could calculate the mean, or like you could calculate statistics of the of P of X, or you could use it to optimize for something like the parameters of a common filter. So that the reason why we care about the stationary distribution is because it, like, we've constructed a Markov chain where we can converge to the stationary distribution, which is P of X. I hope that yeah.
So I'm wondering how I guess wide of a time span does the stationary distribution have to occur over? Because I know you mentioned that there can be multiple converges onto multiple stationary distributions in the chain.
Well, you could only converge to one.
Right.
But so the big thing about MCMC is that the way it's constructed, it converges to a single stationary distribution, which is P of X.
Right. Okay.
How long it takes is a really good question. I think I'm actually going to talk about that now. So as we've kind of seen from these examples here, you have to sample for a while from where you start from in order to get to the stationary distribution. So a good question is like, how long should you sample from from your Markov chain to get the stationary distribution so you can get the samples that you want? So I just wanted to introduce this concept of like, there's a burn-in period where you're sampling from it, and then there's the period when you get to the stationary point. So starting from different states, you may converge faster to the stationary distribution. The likelihood that you've converged increases with sequence length, and we want to minimize the number of sampling steps we want to perform. So that's why the paper talks so much about like different sampling methods, how many sequences to sample, and how long each sequence should be, because all of it's around the fact of like getting to the point where you have samples, which means that you have to have converged. And maybe starting from different states and having multiple sequences can help you converge faster, or just doing one really long one or multiple really long ones, and then different sampling methods help you converge faster. Yeah. Mm-hmm.
What's the, I guess, is there like a prescribed methodology for how do you detect convergence?
Yeah, that's a good question. I talk about it a little bit later, so right, let's talk about it later if that's all right. Okay, so as I said before, different sampling methods have different convergence rates. And so I wanted to talk to you about like the most basic sampling method, accept reject sampling. And this is a method that isn't actually a Markov chain sampling method. It's like the precursor to it, so it converges more slowly. But so how does accept reject sampling work? So the setup is we have f of x, some function, where we know that f of x divided by z, the normalizing constant, is equal to p of x, the probability distribution that we care about. And then we have to choose a proposal distribution, q of x, where we know that f of x is always smaller than or equal to m of q of x. And where m is some constant, and the smaller the constant is, the better, because that means like more closely the two distributions match each other. I think the most common distribution to choose is a normal distribution for q of x. So you have to choose some distribution q of x, and then how do you get samples? So what you do is you get a sample from Q of X, your sample here, and then you sample from a uniform distribution, 0, 1. And if your sample from the uniform distribution is less than your sample is less than your f of the sampled value, x sample, divided by m times q times x sample, then that means you can accept the sample. Otherwise, you should reject. So it's that simple. You just keep doing that over and over again. And the key thing to notice is that the current sample does not depend on the previous sample. And that's why it's not Markov chained. But it is a method that will allow you to get samples from P of X after a certain amount of time. You have to burn in a certain number of samples, and then you have to, and then you can assume that the rest of the samples are actually samples from P of X. So one very important thing is that convergence can never be concluded with certainty, but there are tests you can perform to determine, it's not to determine, to suggest convergence. So you never know, there's no way of knowing with certainty that you've converged. That's just, I think, because this is a sampling-based method, and probably if you're dealing with a continuous domain, it's impossible to explore the whole domain. But there are certain methods that you can use as tests to say whether you've converged or not. So one is the Gelman-Rubin convergence diagnostic. Another is R-hat. There's many more, because it's a very fruitful area to write a paper. And maybe it isn't anymore, but it was. And then there's, so we've talked about accept-reject sampling. But what about, let's talk about like an actual MC method, Metropolis-Hastings sampling. So Metropolis-Hastings, let's talk about how that works. So what's the difference? Ooh, I'll make this red. Sorry, guys. Like I said, I was doing it pretty quickly. Okay. I forgot to change this. So again, we have f of x, where we know that f of x divided by z is equal to p of x, and then we choose a proposal distribution, which is similar to before. So the proposal distribution, we know that like x q of x times m is less than f of x. I mean, it's greater than f of x. But this time, it's a distribution where it's conditioned on the previous state. And the way it's conditioned is that q of x has to be, the distribution has to be centered at the previous state, x of t. That's the big difference between the other method in terms of like the distribution. Before, you just have some distribution that's fixed. Now the distribution that you're sampling from is conditioned on the previous state. And the way that you do it is you sample from your distribution Q. You don't have to sample from a uniform distribution anymore, or Q of t is centered at x of t. And then what you can do is you can calculate these ratios, RF and RQ. And then your acceptance probability is the minimum of 1 or RF times RQ. So if the probability is 1, then you just accept it. And if it's less than 1, then you can sample from that probability to determine whether to accept or reject our x of t plus 1. And you repeat this until convergence. I'm just going to... It's actually... The math behind why this works is pretty cool. I don't want to go into it now because I feel like I'd rather you retain what I've already said than like go into more detail. But that's actually my presentation. One thing I want to say is I think I told you guys something wrong, which is I don't think, and so hopefully someone who is better, I was just thinking to myself, accept reject sampling probably shouldn't converge. Like in the sense that there's no idea of convergence because it's not a Markov chain. These things. So I think that we shouldn't be talking about acceptance rejectance, like convergence for that method. I'm guessing that it's just hard to find. This will give you samples from the correct distribution. It just takes a really long time to get a lot of samples with accept reject sampling. And that's why we created Metropolis Hastings sampling instead. If anyone has an idea about that, let me know. But yeah, so that's the whole presentation. And I hope that the main thing, I hope that my explanation gives you a good idea of like MCMC, like why it's useful, and then what's like the concept, like the theory behind it. The main thing that I'm hoping that I was able to explain was that Markov chain Monte Carlo is a method that constructs a Markov chain which converges to the stationary distribution P of X. And then, I mean, if you look at step 2 and you think this methodology of sampling converges to samples of P of X, I find that kind of magical, to be honest, that this just works. And because Q of X is any distribution as long as it meets that criteria, which you could choose like literally the most uncertain distribution that you could think of, and it should still work. So yeah, I thought this was, I think it's pretty magical that MCMC works. And so for next time, I'm definitely going to cover step 3 or part 3, which is practical Markov chain Monte Carlo, the paper. But I wanted to ask if you guys want me to cover like convergence tests, or why, like the theory behind why the accept reject method and Metropolis Hastings methods work.
I'd definitely want to see like maybe just like a popular convergence test, just to get an idea of like what are the considerations when trying to determine convergence.
Okay.
Yeah. Caterpillar plots. Never seen a caterpillar plot, I don't think.
Awesome. I always say cover. So we'll cover a convergence test. We won't cover why these things work. Maybe I'll see if it's related to all the different methodologies that they talk about in the paper. But my main goal is like now when we talk about like I hope you guys can take away from this why they talk so much about like sampling from one long sequence versus multiple sequences. Like why is that important to MCMC? And also the idea that different sampling methods have different convergence rates. So yeah, I hope those are some takeaways that you guys have from the presentation, and we'll stop here if anyone, unless anyone has any questions.
Hi, Peter. What happens when you reach a stationary distribution?
So when you reach it, all your samples after that should just be part of the same distribution. And before, the samples could be from multiple different distributions. And that's why it's so powerful, because like all of the samples I'm getting are from the distribution that I want to sample from, even though I don't know that distribution.
That would be different distribution from like before and after stationarity. Those would be different distributions, wouldn't it?
Yeah, they would be.
And you would still apply a Metropolis Hastings algorithm to sample from the stationary distribution, or not?
So, yeah, sorry, go ahead.
No, so I was just wondering what sort of sampling method would you use when you reach stationary distribution? So to sample from stationary distribution, what sort of method would you use?
The same one.
The same one, okay.
You just keep doing it over and over again, and I guess you at some point you apply a test to see if you've reached the stationary distribution, and then you can like say, okay, I'll take the last 100 samples or 1,000 samples, and I'll assume they're from the stationary distribution.
Okay.
Yeah, I guess that's right. They should be. That's a good point, Arvid. Because if you're sampling from the same distribution, samples should be IID, right? So the point was that reaching stationary means that samples are quasi-independent. Yeah. Cool. Well, thanks everyone for coming. And next week we'll actually discuss the paper. I'm sorry we didn't get to it this time. I just planned poorly, and I was trying to do too much at once, but I decided to focus more on the basics first because I like covering them as well. But yeah, thanks everyone for coming, and hope you have a good weekend.
Thanks a lot, Peter. That was really cool. Yeah.
Thanks.